This video accompanies our recent paper in which we describe and validate distributed algorithms by which a group of modular robots can self-assemble into bridges across gaps in the terrain. Crucially, we take a force-aware approach, meaning that our robots measure forces within the structure and react accordingly to build strong bridges. We propose a set of novel force-aware self-assembly algorithms and extensively test them in simulation. We also design custom hardware based on the HiMod platform to verify the core concepts of our algorithms in real life. We split the lifespan of self-assembled bridges into 3 stages and develop a distributed force-aware self-assembly algorithm to achieve each. First, they construct a cantilever across a gap from a fixed support on one side. When the other side of the gap is reached, agents can leave the structure during bridge optimization to perform other tasks. Finally, when the bridge is no longer required, it is deconstructed. This consists of 2 phases. Agents first construct a structure that will be stable when released on one side, and then deconstruct this column by column. Our algorithms are first shown in simulation to describe their operation. Agents, shown in blue, initially construct a cantilever from one side of a grey fixed support. Several agents can move concurrently to enable rapid construction. Initially, they gather data about the force distribution throughout the structure when coloured orange, then add themselves to it in a suitable location. They're depicted yellow when moving to these placement locations. Initially, they can build a single horizontal row. However, eventually links will become close to failure. We compare the moment and axial force to allowable limits below the actual failure strength. If a link exceeds these allowable limits, it's described as critical and is close to failure. This is indicated by the link turning red. In these scenarios, an active agent should place to provide reinforcement to the structure, as shown here. A probabilistic method is used to place near columns with critical links to transfer the load to the support. Multiple active agents self-assemble the structure simultaneously. When agents must pass each other, they trade internal states and become one another. This is possible as all agents are homogeneous, and is useful as it removes the coordination required by other methods, such as climbing over each other. Our simulations finish when 100 agents have been placed. Our algorithm is able to reach close to the longest possible stable length for a given number of agents in our tests over a range of link strengths. When the other side of the gap is reached, the bridge will contain more agents than necessary now that it's supported at both ends. In our second stage, bridge optimization, agents leave the bridge to perform other tasks elsewhere. Placed agents become active when they believe they're not significantly contributing to the strength of the bridge. They explore the structure to determine if it's critical elsewhere, then leave it above the right support if it is. This requires them to pass through the structure in the third dimension as shown here, a motion which is otherwise not permitted in our 2D simulation environment. If an active agent finds the bridge contains critical links, it reinforces the structure instead of leaving. We test the algorithm for several lengths and link strengths. It typically results in bridges with close to the minimum number of agents required for a stable bridge of this length and strength. Our final algorithm enables bridges to be deconstructed when they're no longer required. Initially, agents build a structure that will be stable when one support is released. They're added to the structure above the right at regular intervals. Additionally, those left of a narrow section can release when instructed by an active agent, or when they believe they're not significantly contributing to the structure's strength. Knowing where to reinforce the structure is challenging in this scenario, as the force measurements that active agents receive include both supports. To overcome this, we use the structural engineering principle of superposition to subtract the effect of this support from the measurements. Agents can therefore build a structure which may experience high loads while agents are added, but will not collapse when the opposing support is released. Upon the release of this support, agents deconstruct the structure column-wise. Similarly to the other algorithms, this approach is tested for a range of scenarios. While it typically requires more agents than in the original cantilevers, the forces and moments experienced during the deconstruction are typically no more than in the previous stages. To verify these algorithms in real life, we developed a custom force-aware modular robotic platform. This is based on the HiMod design, which utilizes high-gen connectors. These are strong and fast genderless connectors with single-sided disconnection capabilities. We modified the design to include strain gauges to enable force measurements. Agents can move as a meta-module of 2 modules. We performed experiments with these modules to validate our force-aware approach in real life. To focus our experiments on the key force-aware concepts of our self-assembly algorithms, agents did not autonomously move in our experiments. One module is moved around the perimeter of the structure by hand, recording forces and strain gauges of modules in the structure. When it reaches the left end, it decides where to place based on this information. In this case, the allowable force is exceeded, so the next module is placed to reinforce the structure. Column 1 is chosen to place in. A module is placed by hand at the location specified by the algorithm. The actor module is moved around the perimeter again, gathering new force information. All measured forces are below the allowable force here, so the next module can be placed at the tip to extend the cantilever. This process repeats until all 10 modules have been placed. During bridge optimization, the starting configuration is taken from a cantilever trial of the specified length. Agents selected for release are replaced with an active module. As in the real-world experiments of the cantilever construction algorithm, this active module is moved around the structure by hand following our algorithms. It leaves the structure if it measures no critical links, otherwise it will provide reinforcement. Experiments finish when an agent attempts to release in the same location as one just placed. Bridge deconstruction trials begin with a bridge from a previous algorithm. In contrast with simulation, agents are added and removed above the left support, not the right one. Once again, agents are moved around the structure by hand while following our force-aware self-assembly process. The removal phase begins when the agent at the tip is requested to release, and continues until all agents are removed. Although our experiments are not fully autonomous, the HiMod design is capable of the required motions. We demonstrate the ability of a metamodule to walk in several scenarios. First, we show how it can walk over a row of highgen connectors on a simple track. We also tested it walking over and under bridges. The motors are strong enough to move the module as required, and the highgen connectors can sustain these high dynamic loads. However, due to mechanical backlash in the current design, human assistance is needed to ensure proper connector alignment. In future, we aim to demonstrate fully autonomous self-assembly, as shown here. Our work has shown the benefits of force-aware methods of self-assembly, and could be employed in scenarios beyond bridge building to ensure robustness in real-world modular robotic systems. For further information, please see our full paper.